Good afternoon to everyone. This is the last session in today's lecture series, and the lecture is going to be given by Professor Colin from Tel Aviv University, Israel, and the title of the talk is Satellite Sensors for Remote Sensing of the Earth. So, as a chairperson of this session, I welcome Professor Price to our faculty development program. Thank you very much, sir, for accepting our invitation to give your lecture.
You're very welcome.
Thank you, sir. And before we go into the presentation, I would like to briefly give a short introduction of Professor Price so that people can know whom they are having the resource person with. So Professor Colin Price is a professor in the Porter School of Environment and Earth Sciences at Tel Aviv University and the head of the Department of Environmental Studies. He is a world-known atmospheric physicist specializing in the Earth's weather and climate with a focus on thunderstorms, climate change, and natural hazards. His recent research focus is on weather and climate and using atmospheric electricity to study the natural hazards such as flash floods, hurricanes, earthquakes, and solar storms. He was born in Johannesburg, South Africa in 1962. After starting his university studies in South Africa, he transferred to Tel Aviv University in 1982, where he completed his BSc and MSc degrees in geophysics and atmospheric sciences. He received his PhD at Columbia University, New York in 1993 while working at NASA's Goddard Institute for Space Studies in New York. After completing a postdoctoral fellowship at the Lawrence Livermore National Laboratory in California, he returned to Israel and joined the faculty of Tel Aviv University in 1995. He has published more than 140 scientific papers and has a team of more than 10 graduate students and researchers working under his guidance on various scientific research projects. And also he heads the Institutes on Innovation and Transportation and the Institute of Nanosatellites, both at the Tel Aviv University. And I am also proud to announce that Professor Colin Price is having a bilateral collaboration project with our department. And this is a very prestigious project, and we are very lucky to have Professor Colin Price today as a resource person on this faculty development program on sensor technology. I now hand over the mic to Professor Price to kindly deliver his talk. Sir.
Thank you, Annie. Thank you very much for that introduction. Can you see the screen? The image of the satellite on the screen? Am I sharing my screen correctly?
Yes, we can see that.
Okay. Good. Okay. So thank you. I'm very happy to be here and to give the lecture today. This is a slightly different lecture that I normally give because, as Dr. Guha mentioned, we're working together on electromagnetic measurements of lightning and thunderstorms at the Earth's surface. And today my talk is going to present more about sensors from space, from satellites, and today there's also a movement into what we call new space, where students like you can actually build small CubeSats or nanosatellites and launch them into space within 2 years or so. The costs are a lot smaller than normal satellites, and this allows us also to use these small satellites for research purposes, and so there's maybe even a revolution in the space industry, in the civilian space industry, where it was much too expensive, it took too long, and you needed huge teams to build satellites in the past. And in the present and the coming years, including India, there are many students and universities which are building their own satellites now and sending them to space. So we'll speak a little bit about this today, about how we actually get information, scientific information, when we're looking from space. So let's start off, and if there's any something you can't see or problems, just please open your microphone and let me know. And also, if I'm happy to take questions along the way. So let's go to, yes.
So Your presentation is not completely visible. It is partial.
What does that mean?
Now it is okay. But when you go to full screen, I think this mode is okay. If we
this
can
mode's
continue.
okay?
Yeah.
Okay. So you can see this mode?
Yeah. We can see
okay.
this.
Okay. So we first need to define the difference between direct measurements, or what we call in situ measurements, and remote sensing, which are indirect measurements. The in situ measurements are measurements when you're actually inside the medium, inside the air, inside the atmosphere. And we can see in this picture instruments to measure, sensors to measure wind speed. Inside here we have temperature, humidity, other sensors. But without seeing the data at the bottom, you wouldn't know if this is a very cold day or a very hot day. We have to really be inside and to actually measure the air temperature, the molecules, the wind speed, the motion of the gas, to know something about the physical state. Remote sensing means that we can actually look from far away at the medium, at the surface of the earth, at the sun, and get some information. We're actually sensing the information from far away, remotely. And
Colin,
we can actually look.
I'm sorry to interrupt you again. There may be some issues in the having a view of the full presentation. So can you again try in full mode and let us see whether we can see the full presentation?
Can you see this? This is the full mode.
Okay, so let me ask, I ask the participants to say yes or no in the chat box if they are able to see the screen properly. Then we will go ahead with that. Yes, okay. Yes. Please participate, you can please no, yes, okay. Shekhar Chakraborty, no. Some people no, interesting. No PPT screen. If some are saying no PPT screen, that means you did not share, actually pin the screen actually. I think you go ahead. Yes, you can go ahead.
Anirban, can you see the screen, my screen?
I can now see the screen and okay. PPT is there. Yes, you can go ahead.
Okay, if you want, I can also go through Zoom. If we want to do it on Zoom, I'm not sure if it's any easier.
But we make all the participants to migrate to Zoom right now. So,
okay. No.
But I think now people have said yes, so people can see that. I think we can go ahead.
If there's any problem, you let me know.
Okay, I will let you know. Sorry for the interruption.
Okay. No problem. So on the right, we can see here that remote sensing, when we're using our eyes, we're looking at this boiling pot of water. And I think most people would agree that the water was very hot here. And this is because we can see a few different things. We can see, first of all, that the red stove below, we can see the water is boiling. We can see the steam above it. So these are parameters which we can actually measure from far away, and it will tell us something about whether the water is hot or cold. On the left, we don't know if the air is hot or cold because there are no other indications except being inside the medium. So when we talk about satellites, most of the sensing from satellites is remote sensing. We're far away from the surface of the Earth, from the atmosphere. We have to get some information from far away. Although there are some satellites which give us in situ measurements when we're measuring, for example, the Earth's magnetic field, or energetic particles which are coming in from the sun or from cosmic rays and are colliding with sensors on our satellite. So some satellites do have in situ measurements, direct measurements, but most are indirect. Okay, so we're going to talk mainly about the remote sensing, which means where the satellite sensors are not inside the medium, and we want to get some information remotely. And so when we try to do this, there are a number of different things we have to worry about. First of all, we need to know for example, the source. What's the source of the emission of radiation that we want to detect? Are we talking about the sunlight, which will be either directly observed or reflected off the Earth's surface? Are we talking about emissions from the Earth's surface, or from the oceans, or possibly even from another satellite? Like the GPS satellites are used now as a source, giving the GPS signal, and other satellites can detect them and study something about the atmosphere using that as the source. We need to know something about the medium in between the satellite and the source. This is normally the atmosphere of the Earth, so we need to know something about the atmosphere and the transmission of the radiation through the atmosphere. We need to know something about how that radiation will interact with both the Earth's surface, with gases in the atmosphere, with aerosols, particles, clouds, and also absorption by those parameters, but also scattering of the light. So the light may be scattered off clouds. We need to understand how clouds scatter, and from actually detecting this radiation, we may be able to say something about the cloud droplets, the cloud, if it has ice, the size of the particles, etc. Now, when we're talking about satellites and remote sensing, we normally talk about two different classes of sensors. We have active sensors and passive sensors. When we talk about active sensors, we're talking about sensors where actually we have to produce and transmit a signal, and then we'll get that signal reflected back towards us. For example, radar, cloud radars, which send out a pulse and we get a reflection off the cloud or off the surface of the Earth, of aerosols. You can use lasers, radars, wind profilers as well, where you send out a signal and it gets scattered off the atmosphere, tells you something about the winds. These are much more expensive and more complicated sensors because you need to have some transmission of a signal as well as receiving the reflected signal. But many satellites are passive sensors, and passive sensors basically only receive the energy coming out of a cloud, coming out of the oceans, from the sun, reflected off the surface. So the sun is normally our main source of energy, and it gets reflected off forests and off the land and off the oceans. And that reflected energy we can detect, and from the reflection say something about the surface parameters. But the satellite is only passive. It's only receiving information. It's not transmitting any information to the surface. Now let's talk about different types of satellites. Here too we have two different types of satellites. The first one is what we call the GEO satellites, GEO for geosynchronous or geostationary satellites. And these satellites are around about 36,000 kilometers above the Earth's surface. And the reason that they're there is because when we put them at that location, their velocity, which is basically resulting in centrifugal force pushing them out, equals exactly the gravity, and therefore we don't need any fuel for these satellites to stay in the same point. And at that altitude, the time it takes for the satellite to do one revolution is also 24 hours, exactly the time it takes the Earth to rotate. And therefore, from the point of view of the satellite, it's always looking at the same point on the Earth's surface. And therefore, we can look at things which are changing over time, fairly fast time. And it turns out that these satellites, in order to do this, for them to be located over the same location continuously, the satellites have to move at about 3 kilometers per second. And because of that, as you see in the animation, they're constantly seeing the same footprint of the Earth. As a result, we can actually take pictures and snapshots fairly rapidly, normally around about every 15 minutes, but you can have rapid scanning of maybe every minute if you want to look at the development of thunderstorms or something which is changing very fast. One of the problems of the geostationary satellites is being so high up in the atmosphere is that the spatial resolution is fairly coarse at the surface. You can't really see anything better than a few kilometers, maybe, the pixel size at the ground. And so we can't really use them to looking at very fine resolution images. But because they sit above the same location and we can take many pictures in the same location all the time, they're also good for looking at animations. You can produce animated GIFs to see actually the dynamics of the atmosphere of the Earth, how clouds are moving, how they're developing, how things change as a function of time, even very rapidly over minutes to hours. And the final problem, everything has pros and cons. Every sensor has some pros and cons. And another one of the problems is that because they're located basically over the equator, going around the planet at the same location, we don't have a very good view of the polar regions. So if we want to study the pole, the North Pole and the South Pole, geostationary satellites aren't very good for that. Today we have many geostationary satellites around the globe, and they're all located on the equator, but at different longitudes. And most of these are used for communications, for television, transmitting, and because they're so high up, we can transmit TV shows and communication, cell phones around the globe using these. And different countries have different slots where you can actually put your satellites. There's specific regions, longitudes for India, for the Europeans, for the Americans, but it's becoming fairly compact here, and there's a lot of traffic up there. And once your satellite actually ends its life, maybe 25 years, that can live up there, you have to actually deorbit it or move it to what they call the satellite graveyard in a higher orbit so that you can bring in new satellites to the same location. The second set of satellites are what we call LEO, L-E-O, for low Earth orbit. And these are much lower down, between 400 and 1,000, but around about 800 kilometers. It depends on satellite. There's no fixed altitude. And here, these are much faster because the force of gravity pulling the satellite in is stronger. So they have to go faster to keep it in equilibrium at the same altitude. Around about 8 kilometers per second, the LEO satellites are traveling around the Earth. This implies that they do an orbit. They go around the Earth once every 90, 100 minutes. So every hour and a half, they can do one orbit around the planet. And how they're actually planned is that they go in a single orbit, but while they're going in the orbit, which is normally planned from north to south, unlike the GEO, which are going around the equator, the LEO satellites are normally going from north to south at some angle. The Earth is rotating underneath them. And so every time the satellite comes over, as you can see in this animation, it takes an image of a different part of the globe. And so this is good for looking at the many different places of the globe, including the poles. Unlike the GEO, we can see with LEO satellites the ice caps and what's happening over the North Pole and the South Pole. So we can get a picture of what's happening over the whole planet. Because they're low down, we have a fairly good spatial resolution. We can put cameras on which can give us very good resolution down to meters even. And but the disadvantage is that we have poor temporal resolution for the same location. So these satellites are not good for monitoring, say, thunderstorm development or cloud development, because they take a snapshot and then they're gone. And an hour and a half later, they come back to a different part of the planet and don't see the same thunderstorm. So again, there are pros and cons of each type of satellite, and depending on what research you want to do, you choose your satellite. So we have the GEO satellites, which are far out, 36,000 kilometers, and around the equator of the Earth. And then we have these LEO satellites, which are around about 850 kilometers. Now, today, nearly every country has their satellites up there. Some of them we know about, some of them we don't. And we're starting to see problems with what we call space junk, and just too many satellites. And again, satellites and rockets, which they die out, their debris remains in space. And we have space debris and sometimes accidents of things hitting other ones. And if we can go to this website, which is actually very interesting, which actually shows, I hope you can see this, showing where the space junk, all the different pieces which are seen in space. Can you see this this plot, this animation? If we look at the different dots here, each dot on this map, on this plot, represents a different piece of space debris. We can zoom out, and we can see here the geostationary orbit close to the equator. And if we come closer to the Earth, you can see the cloud of debris around the Earth, which is from the LEO satellites. And we can actually click on any one of these, and we can get some information. Let's come closer here. It normally tells you what this is, but you can see the name of what rocket and the different colors represent if it's an active piece, active satellite, or some debris from a rocket. And there's a huge amount of debris out in space, which is becoming also a problem. He has a Landsat satellite, and if we move in, you can actually see that they're moving. So you can actually see that they're moving in orbit constantly. These are tracked by the American and the Europeans to make sure that there are not going to be any accidents or any collisions. But this is becoming more and more of a problem, and this could be some of the solutions could be found by you, some of the young scientists, future, how to clean up space from all this junk. You can see this coming over India. Okay, let's go back to the presentation. Okay, so if we want to look at the geostationary satellites again, being so far out in orbit, we actually get to see the whole disk of the planet because we're 36,000 kilometers away. And these are two views from the American goes east and the goes west. Goes west is over the equator and in the middle of the Pacific to see the western part of the United States mainly, and all the storms which are coming towards the United States. And the goes east is over the equator and I think South America to see the eastern side of the US. To get a global coverage, again, one of the disadvantages of this geostationary satellites is we cannot see the whole globe from one satellite. It's always located just over one spot. So on the other side of the planet, we need to put another geostationary satellite if we want to complete the picture. And so here we can see to get a global image, we need to really take a few different geostationary satellites. The two Americans, the Meteosat, are the ones over Africa for the Europeans. We have here also the Asian, the Indian, and the Chinese satellites. And we can put all of these together and merge them, mesh them together to get a global image of clouds at any time. So this took a few days ago, the 19th of September. And you can see here where the clouds are occurring. And there's a link here which you can go into to see the latest images from the last few hours even, if you want to see the real-time data of where clouds occur around the planet. Now let's talk about the sensors on the satellite. So we've got the different types of satellites. Now let's talk about sensors, and these sensors can be on any satellite. And we can again break them down into different parts of the electromagnetic spectrum, and primarily between the visible and the infrared. The visible part of the spectrum basically is what we can see. And when we talk about what we can see, it's what is reflected off the surface by sunlight. So visible sensors are basically detecting the reflected sunlight from different objects, and we call this the albedo. So the albedo is how much of the sunlight coming in is reflected back to us. And this is normally measured in percentage. So fresh snow, white snow will reflect maybe 80 to 95% of the incoming radiation, while dark forests, the rainforests, will reflect maybe 10 to 20% of the radiation. And if we go into the oceans, maybe 10 to 60%, and it's quite variable because of the angle of the sun. So when the angle of the sun is more or less perpendicular, then very little gets reflected. The oceans are very dark. But as we get to sunset or sunrise or even high latitudes, then you can have some more reflection off the surface, and it can go up to even to 60%. And when we look at the surface, different colored, the asphalt from roads is very dark. We know dark colors will absorb more. Ice sheets will reflect more. Agriculture and cities are maybe lighter in color. And so by looking at the reflected visible light, we can say something about the object we're looking at, including, say, the moon. And here's a visible image of the Meteosat geostationary satellite. So we can see here, this is what, it's a black and white image, obviously, but this is what we would see with our eyes if we were sitting on the satellite and we converted it to a black and white image. We see that we have the darker areas which have got the lower albedo. The oceans are reflecting less, so they're dark. The lighter colors are the desert regions, the Sahara Desert, and the white areas are where we have clouds, which are white in color, so they reflect a lot of sunlight. And this is what we would expect to see: the darker colors from the oceans, the whiter clouds, the lighter deserts, and the darker forests, which we see in the central parts of Africa. So when we look at visible reflection, we can't really look at the whole spectrum. And so when we're looking from satellites, we need to design our sensors. And often we look at the peak of the solar radiation. This is the spectrum of the solar radiation. The yellow is what comes in from outside the atmosphere, and the red is what we will detect at the surface. And we see that the peak is in the visible. We have some ultraviolet, that's what gives the suntan. When people go sunbathing. Infrared is the heat we feel from the sun, but the maximum radiation is in the visible. And therefore, when we design visible sensors, we normally design them around about 0.5, 0.6 microns, because this is the maximum radiation, incoming radiation from the sun. And therefore, we want to see how much of this maximum will be reflected back to the satellite from different objects in the atmosphere and the surface, from clouds, land, and sea. One big problem with visible sensors is that we can only see during the daytime. We don't have visible light from the sun at nighttime. And so satellites can only really see the reflection of the sunlight during the daytime. And so only 12 hours of the day, really, do we get information with visible sensors. But it still gives us some interesting information. Again, the dark areas where we have small amount of reflection. This is where we have the dark oceans, the forests, and we have low albedo. And the light areas are where we have a high reflection, the desert regions, the clouds, snow, ice, and this is areas which have high albedo. Now, after the visible, we can also talk about the infrared. And infrared is sometimes more interesting because it tells us more things, and we can see this also 24 hours a day. So infrared is basically the heat which is given off by any object when we're looking at the Earth or the atmosphere. And it basically tells us the temperature of the emitting substance. If it's the surface, if it's the ocean, if it's clouds, if it's forests. The infrared radiation is related directly to the temperature. We'll talk about that in a second. And when we're talking about clouds, the temperature of the cloud also says something about the altitude, how high they are, at least the cloud top in the atmosphere. So the colder the emission from the top of the cloud, the higher it is in the atmosphere, and the warmer it is, the closer it is to the surface. So this also gives us information about the vertical distribution of clouds in the atmosphere. So here's an infrared image for the same image we saw before. In the visible, we can now look with the infrared sensor, and we see here that now we're seeing an image of temperature, where the black is the hot temperature and the white is the coldest temperature. And as we would expect, the desert regions in northern Africa, and this you can see the time, this is 12 UTC. This is taken in May 2010. So 12 UTC, the peak of the radiation from the sun. And we can see the darker regions are where we have the hottest temperatures. And the coldest temperatures are the clouds, and the very whitest temperatures are where we have the coldest temperatures or the highest clouds. And these are thunderstorms which are developing over Africa. We see the oceans are more grayish color, unlike the visible where they were dark because they absorbed or they reflected small amounts of solar radiation. In the infrared, they're emitting less heat than the land because they're colder. So we get the grayer color in the ocean because they're cooler than the land areas, but the clouds are a lot colder than the oceans. Now let's talk a little bit about infrared radiation. I'm sure most of you as physicists studying physics, you know about black body radiation. So we'll just give a little bit of a background here. And it's always good to go over something that you already know. So this will refresh your memory. But basically, all substances will radiate energy as long as the temperature is above absolute zero, 0 degrees Kelvin. Nothing can get to 0 degrees Kelvin because you have to have something colder than that. And therefore, everything in the universe will emit infrared radiation, not necessarily infrared, will emit radiation. And it's interesting that when we look at gases, whether it's in space or in our atmosphere, they radiate at specific frequencies, so they have specific wavelengths, while solids have a continuous spectrum. So they have a solid continuous spectrum. And so this is also one way we can tell the difference between whether we're looking at a gas or looking at a solid, because of the shape and the spectral lines we see in the spectrum. Now, the black body radiation, you've also, I gather, learned this, is determined by Planck's law, which describes the radiation of a black body as a function of temperature and frequency. And it's derived from the probable molecular energy distribution at any given temperature. So this big B here is basically the flux of energy, the radiation given off as a function of the frequency and the temperature of the body. And here we have Planck's constant, the speed of light, Boltzmann's constant K, the temperature of the body, frequency. And if we integrate over this as a function of frequency, so we integrate over all the wavelengths and all the frequencies, but we just leave the dependence on temperature, then we get a very simple law called the Stefan-Boltzmann law. The Stefan-Boltzmann law leaves us then the radiation as a function of temperature, and it's simply a constant, sigma times the temperature to the fourth power. This is the Stefan-Boltzmann constant, shown at the bottom here, in watts per square meter per degree Kelvin to the fourth power. And we can represent this as a flux of energy, F. And as you can see here, this depends only on the temperature of the body. But it's very sensitive to temperature to the fourth power. So a small increase in temperature, a huge increase in the emission of the black body radiation, the brightness, the radiation from the body. And as it cools like the clouds, as they go up in the atmosphere and they get colder, we have a dramatic decrease in the flux of energy being emitted out to our sensor at the satellite. And we can use this also again to understand what we're seeing with the remote sensing. Another interesting law is Wien's displacement law. If we go back to this relationship, and now instead of integrating, we take the derivative and put the derivative to 0, looking for the maximum. Then we get Wien's displacement law. We do dB lambda or frequency equals 0, and we get a very simple inverse relationship between the maximum wavelength where we have the emission of the radiation. We said from the sun it was around about 0.5, 0.6 microns, and the temperature of the body which is radiating. So a very simple relationship where lambda is given in microns, 10 to the minus 6 meters, and temperature is in Kelvin. And this is the displacement law, because as we change the temperature, we shift the spectrum, we move the spectrum, we displace it to shorter or longer wavelengths, depending on whether we're warming or cooling the object. So the wavelength of the maximum radiation that we're going to detect by a sensor depends on the temperature of that body which is radiating, and inversely proportional to that. So the hotter the object, the higher the frequency, or the shorter the wavelength of the emitted radiation. And we know that the Earth's temperature is basically 288 degrees Kelvin, about 14, 15 degrees C. And therefore, based on this displacement law, we can assume that the maximum emission from the Earth is around about 10 microns. This is in the infrared part of the spectrum, and therefore, when we look at the Earth with our sensors, again, we don't see anything during the nighttime because the Earth doesn't radiate in the visible part of the spectrum. It radiates in the infrared part of the spectrum, around 10 microns. On the other hand, if we look at the sun, we can't really measure the temperature of the sun, but we can measure where the maximum wavelength is, and we said it's around about 0.5 microns. It's more exactly 0.48 microns. If we put that into the equation here, we see that the temperature of the surface of the sun is around about 6,000 degrees Kelvin. And if we look at this again, this yellow curve, the yellow spectrum of the sunlight coming to the Earth, we can see this black line is the Planck function for an object around about 5,778 Kelvin, or close to 6,000. We see it's not an exact match. We could raise it up a bit to warmer temperatures here, but then we lose some of this. And this is because actually in the atmosphere of the sun, some of this radiation is absorbed by the atmosphere and doesn't make it out in the UV part of the spectrum. But it's a fairly good approximation that the surface temperature of the sun is around about 6,000 degrees, which matches nicely this spectrum of emission, which has a maximum around about 0.48, 0.5 microns. And if we look at theoretical Planck functions, we can see here wavelength in nanometers, and this is the power density, the emissions. We first of all see the different curves are different temperatures, bodies at different temperatures. And so we basically can go from here, we have 3,000 degree, 4,000 Kelvin, 5,000, 6,000. The 6,000 again is similar to the sun's black body radiation with a maximum around about 0.48 micron or 483 nanometers, with a peak here in the visible part of the spectrum. But as the objects get cooler, we can see that the peak is shifting. This is the Wien's displacement law. They're shifting towards longer wavelengths. So a body of 5,000 degrees will have its maximum emission around about 580 nanometers. If we come to 3,000, we can see that the maximum emission is about 724 nanometers. And the same if we go to a hotter objects which are hotter than 6,000, this peak will shift towards shorter, will be displaced to shorter wavelengths. So that's the displacement law, but then the actual amplitude, the magnitude of this peak, as you see, as the object gets warmer, it gets higher and higher, and that's the Stefan-Boltzmann law, the sigma t to the fourth power. Small change in temperature, a big change in emissions of radiation. A few other concepts. The emission of a substance, like the Earth's surface, depends on what we call the emissivity, this epsilon, of the surface or the atmosphere. So what actually makes it out of the object or out to space depends on the black body radiation leaving the surface, but also what is absorbed along the way or what is transmitted through the atmosphere. So the emissivity will be 1 for a black body, implying that everything will be emitted out, and it will be equal for every frequency. So epsilon equals 1. And that'll be a black body. So everything coming in will go out. But if we look at a gray body we can define as a body which has epsilon less than 1, but for all the frequencies. And then if we want to change the color of the object, we can have this emissivity being different for different wavelengths. And so we want to know something about the emissivity of, we can understand something about our atmosphere, the surface. If we're looking out at space, we're getting this emission, we know what it should be, and we can say something about the medium in between, the emissivity, both of the surface and the atmosphere. And another important law is Kirchhoff's law, which says that in thermodynamic equilibrium, in other words, when the temperature is constant, the incoming and the outgoing are reaching some balance, the emissivity of a substance must equal its absorptivity. So anything which absorbs nicely will also emit well. A black body takes in all the radiation, but it also emits it out to space. And so we know that, for example, wearing a black t-shirt absorbs a lot of radiation, but it also emits a lot of heat. White objects will absorb less and will actually also emit less. That's Kirchhoff's law. So let's go back to the infrared radiation. If we want to look at the Earth now from space, we said that the Earth's maximum radiation out to space is around about 10 microns. And that's because of the temperature of the Earth. The temperature of the Earth, and if we look at the Wien's law, 10 microns. And if we actually look what happens in practice, we can see the theoretical emission, Planck's emission for a 288 Kelvin object like the Earth would be the yellow curve. This is the expected spectrum. What we actually see if we're looking at the Earth from space is the red part of the spectrum. It does peak. We see most of the emissions are around about 10, in between 8 to 12 microns. We call this the atmospheric window because most of the radiation and the cooling of the Earth is through this window. But wherever we don't see the red, the yellow area, this is where the atmosphere is actually absorbing the radiation given off from the surface. Most of this absorption is due to water vapor. We can see over here, these are the wavelengths where water vapor absorbs, but also carbon dioxide, some methane. And this is what we call the greenhouse effect. The Earth's atmosphere traps in the heat. These molecules trap in the infrared radiation, heat up the Earth, does it naturally as well. And this heating actually warms up the Earth from what would be minus 18 degrees, the average temperature of the Earth without the atmosphere, to plus 15 degrees, 33 degrees warming because of this greenhouse effect, the natural greenhouse effect, which actually allows us to have liquid water on the planet Earth. If we had no atmosphere, the oceans would be solid ice because the average would be minus 18 degrees. So we can see here that if we want to design a sensor to look at the emissions, this has to be around about here, and therefore the infrared sensors are between 10 and 20 microns. That's what you can see here in the image. I think around 11 microns. And this observation, I hear some noise. I don't know if Anirban, can you hear me? Everything okay still?
Yeah, we can hear you. We can hear you.
Okay, there's some interference there.
We are looking at the interference. We are looking at the interference. Let me see.
Okay. So this depends only on the temperature of the emitting object. And as you see in this image again, the cooler objects, like the high clouds, the white clouds, are shown as light gray or white. And the warmer objects, which are giving off more radiation, are the low clouds or the oceans, the desert regions. And the big advantage with infrared imaging is that there's always some emission from the surface of the Earth, and therefore we're not limited only to 20 to 12 hours in the daytime like the visible. We can see the infrared 24 hours a day, the emissions from the Earth's surface, and therefore we can see what's happening all the time anywhere on the planet. So let's compare exactly these two, the same images, the same time, the same location, visible on the left, infrared on the right, and you can see the differences in the images. Visible is what we would expect to see, brighter surfaces in the desert regions, but much hotter regions. So in the infrared, these are the hotter regions. In the visible, the oceans are darker because they absorb more solar radiation, less reflection. But in the infrared, they're cooler, and so they emit less energy out to space. And so it should be clear that when you look at images, you can tell if it's an infrared image or if it's a visible image just by comparing, say, the land areas and the ocean areas. Now, if we look at these two images, on the left we have a visible image, and on the right we have an infrared image. And if we look at the different clouds by the green X and the red X, I would normally ask the students what they can conclude from this image, but since the communications is not that easy, I'll just give you a few minutes to think about what do you think the difference are between these clouds under the red X and the green X. And what we see is that in the visible, they look kind of similar, and that's because these clouds are fairly white and they're reflecting solar radiation. But when we look in the infrared, we see that these clouds kind of disappear under the red X. We can still see them in the green X. What this means, and the colors, the temperature scale is shown at the bottom here. So the white here are the up to minus 75 degrees C. This is not Kelvin. And the warmer areas are closer to 15, 20 degrees, where we can see actually the surface. And what this tells us is that the red X is above areas where we have low clouds, low altitude clouds. They're white in color, so they reflect the solar radiation, but they're very warm. They're close to the temperature of the Earth. It could be fog close to the surface, which have got warm temperatures, but they're still white and they reflect solar radiation. Under the green X, we can see we have also bright clouds, but in the infrared, they're much whiter, much colder, implying they're much higher in the atmosphere. And so these are likely thunderstorm clouds, which are much higher, much more developed. They're penetrating much higher into the atmosphere. And these clouds are much more likely to maybe produce rain, hail, lightning, compared with these ones. If we just look at the visible, it's not that easy to tell the difference between these clouds. When we need to combine the two sensors in order to see them. And many researchers and even operational weather forecasters combine these two different sensors. We can see here the infrared value. So you can go back here, and for every pixel, you can actually say, okay, what's the value in say a grayscale? Going from 0 to 255 grayscale, what's the grayscale in the visible and the grayscale in the infrared? And then you can come here and you can have from 0 to 255 for the visible image and for the infrared. And when we have, and then you can decide what type of clouds you have. If you have a very dark area in the visible and it's actually very warm, it's pretty certain we're seeing the surface of the Earth. If we're seeing a very bright clouds, but they're warm clouds, then they're low clouds. If we're seeing bright clouds, but they're very cold in the infrared, then this is deep convection. And if we're seeing very cold clouds, but they're actually dark in the visible, these can be very thin, wispy cirrus clouds, which won't produce any rainfall, but they're still very high in the atmosphere, ice clouds, but not very thick. And so they let the sunlight come through them. So often we have to combine different sensors in order to have a better understanding of what's going on in the atmosphere. Now, how do we measure gases in the atmosphere? We've spoken about looking at solid surfaces, the Earth's surface, clouds, but how do we actually look at gases? And so, again, we need a light source. The light source can be the sun or could be something else. And then we know that any light source like the sun is made up of a certain continuous spectrum. If we have a gas which is emitting and not a very dense surface like the sun or the Earth, a gas is emitting, and this could be if we're looking at a star from far away or some gas, hot gas, say in the atmosphere, then a gas will actually emit at specific wavelengths or frequencies, not continuously. As I mentioned before, gases emit with very special signatures. And if we now have a light source like the sun shining through a cold gas, then this gas is going to absorb some of this radiation. And what we see is absorption lines. So we have this spectrum from the source, but at the same place where we have emission, normally of the hot gas, we'll have absorption by the cold gas. And as we said with the Kirchhoff law, something which emits good well at this spectral line will also absorb well at that spectral line. And therefore we get a fingerprint, really. We have a fingerprint, a spectral fingerprint for every gas. We know what the spectral absorption lines for water vapor are, for carbon dioxide, methane, ozone, and therefore we can develop a sensor which is looking either at specific wavelengths or over many, many wavelengths, and then we can look for many different gases in the atmosphere too, if we want to study how the concentration varies spatially or temporally with time. One of the main gases, or the greenhouse gases we're interested in, is water vapor, but also carbon dioxide. So here we can see actually the transmission of different wavelengths through the atmosphere. 1 means 100% transmission, and 0 is no transmission, as a function of wavelengths from about 1 to 28 microns. And what we see is that here, where we have close to 100, we have actually very high transmission, maybe 95% of the radiation between, say, 11, 12 microns will go all the way through the atmosphere, only about 5% absorbed. But here, around about 6 microns, we'll have a very large absorption by water vapor. And so we get these absorption bands in the atmosphere. You can see these big dips here are where we have absorption mainly by water vapor. Here we have a big carbon dioxide absorption band around 15 microns. There's an ozone one here. All of these additional bands are from water vapor. It can be extremely complicated. And so sometimes we cannot measure all these bands in the atmosphere. So we try to design our satellite sensors around a specific band which is only related to one gas. For example, water vapor around about here. If we're looking for carbon dioxide, we'll maybe use 15 microns. And if we want to use ozone, maybe somewhere around here. And so we also have now water vapor sensors on geostationary satellites. And here you can see an image of water vapor. What we're actually seeing here is the absorption of the infrared radiation leaving the Earth, coming to our satellite sensor. And wherever we have the black regions, we're having more radiation or drier conditions. So more radiation is leaving the Earth. And where we're having the gray and the white areas, we have less radiation making it out of the atmosphere to our sensor, implying we have more water vapor in the atmosphere. And here we can see quite it's very continuous. You can think of this as kind of as a fluid flowing around the planet. We don't see this water vapor with our eyes, but when we look with the infrared imager, we can actually map out the different circulation patterns, the storms, the drier regions. And you can see that even over the Sahara Desert, which is fairly dry, we still have water vapor in the upper atmosphere, although it doesn't produce rainfall. So wavelength is an equivalent of saying information when we're talking about remote sensing. When we change the wavelength of our sensor, we're changing what we're seeing, and we're changing the information. So the visible, we can see again now the 3 different images taken exactly the same time, same location, but using different wavelengths. And here we can see the visible reflection, the albedo at about 0.5 microns gives us more or less what we would see in a black and white photograph taken from space. 10 microns tells us about the temperature of the surface and what's emitted from the Earth, and the hotter areas in black, the cooler areas in white. And here we can see the water vapor absorption around about 6 microns, which shows that even over the hot and dry areas, we still have water vapor, and basically you have water vapor everywhere. It's basically a fluid which is traveling everywhere. I should point out that this emission or absorption is more sensitive to the middle part of the troposphere. So it is kind of an integration of the middle atmosphere. And it doesn't give us very good spatial altitude resolution. We don't know if this is really close to the surface, in the middle, or the upper atmosphere, just from this one measurement. As I mentioned, what's nice with geostationary satellites is we can make animated GIFs. We can actually take the data this is every hour, and we can actually result in an animation, and then we can see the beautiful dynamics of our atmosphere. We can see how things are moving around, how these storms are moving over Africa and developing in the afternoon hours, moving into the Atlantic, and maybe even forming tropical cyclones. In the higher latitudes in Europe and the southern hemisphere, we can see the flow going in the westerly direction. And I guess you can figure out that this is an infrared image, because first of all, if you look at the clock at the bottom, we're looking at the entire 24 hours. And you can see the change in the temperature of the continental regions, the northern part of Africa, southern Africa, which are heating up in the daytime, they become black around about noon, very hot, and then they cool down at night. And you can see this daily cycle of the heating and the cooling of the land, but the thunderstorms and the clouds keep on developing and can last for days at a time. The thunderstorms also peak in the afternoon hours, so when it gets black in the north and the south, you'll see more thunderstorms developing and popping up, but they're moving with the general flow of the easterlies, the trade winds, from east to west in the tropics. And with the westerlies, the storms are going in the northern hemisphere and the southern hemisphere from west to east. So there's a lot of things you can learn about the atmosphere, the dynamics, the physics, the climate regimes when we look at using geostationary satellites, where we can get these animations showing actually what's happening, the motion of the atmosphere. Okay, so we've looked at some basics of the satellites and sensors. Now we're going to look at a few examples before I end, some examples of how we can actually use this, beneficiary for both mankind, for our scientific research, for even political debates like climate change today. And lots of things are happening around the Earth, and satellites have helped and are helping to monitor our environment all the time. Here you can just see many things which we can monitor from satellites, including the source of all of the energy coming from the sun, and then what's happening in our atmosphere, the gases, the aerosols, the clouds, cloud structures, the water cycle, rainfall, oceans. We can measure the ocean currents and what's happening in the oceans, sea ice, land ice changes, cities, how our cities are changing over time, agriculture at the surface, vegetation, ecosystems, many different things. And satellites give us a global view. Because they're orbiting the planet, we can get data from all locations on the planet, and the satellites will eventually come back to the same location if they're the LEO satellites. And if they're the GEO satellites, we can actually monitor continuously different parts of the globe all the time. So let's look at a few things. Let's start with monitoring our sun. So our sun is basically the source of all our energy, and so it's important to know what's happening on the sun. On our sun, we have these sunspots which form. You can see a zoom into the sunspots, which are very large. This is a relative size compared with the Earth. And we know now that if we look at these sunspots and we count them using satellites, we see that we go through an 11-year sunspot cycle. The sun becomes more active and less active on an 11-year solar cycle. We're now, at this very moment, at the we need to complete this, but we're at the end of the last solar cycle. We're just starting at our new solar cycle, but so we're in the bottom here, and in another 5 years we'll again be at the solar max. Using satellites, we can actually see how that impacts the solar radiation coming to the Earth. That we're talking about climate change, the weather, everything is driven by the solar radiation. So we can count the spots, that's one thing, but we can actually measure the flux of energy, given here the total solar irradiance, measured in watts per square meter outside our atmosphere, so hitting a sensor outside our atmosphere before the atmosphere has impacted that radiation. And we can see the different colors of different satellites, but we see here that there's a link between the sunspot cycle, the solar cycle, and the actual total solar irradiance, which is reaching the Earth and leaving the sun. We see that when we have a sunspot maximum, we have maximum radiation, but we also have the maximum variability, a lot of noise and variability even from day to day, week to week in the sun. Whereas at the solar minimum, like we are today, the sun is fairly quiet and stable, not too much variability. So we can actually study the variability of our star, the sun, on different time scales using satellites, both on short time scales, also on the long time scales. And some people have claimed that there's a link between the solar cycle and cloud cover on Earth through modulation of cosmic rays. This is still a very debatable topic, but having the information about how the sun varies on short and longer time scales, we can also look for links with the Earth's climate. The sun also experiences many storms. This is a satellite looking at the sun, where actually we're covering the sun with this disk. The size of the sun would be more or less this white circle, and we can then see what's happening around the sun and the atmosphere of the sun. You can see some stars in the background during this time lapse. We can see the date here at the bottom. And what we can see, these clouds of particles which are flying off, is what we call the solar wind. The sun actually produces a wind of electrons and protons, which are actually going out in all different directions. And sometimes there are actually storms on the sun where you can see these big clouds of particles which are being emitted, what we call coronal mass ejections. And they go out in all directions. And some of these particles, they're charged particles. When they actually come to the Earth, they get diverted by the Earth's magnetic field to the polar region. And that's what produces the aurora borealis, the northern lights, as well as the southern lights, when we have the nice aurora displays in the north and the south. These particles are traveling at hundreds of kilometers per second. So they're extremely energetic. Today, there's big worries about how these particles impact satellites as well, direct impacts, but also induced currents and short circuits, and actually changing the friction of the atmosphere with the satellites. And these storms on the sun can even result in strong variations of the Earth's magnetic field, which can generate currents in the surface and even power outages in electric power lines. And so there's a lot of interest on the applied side of solar storms and what we call space weather. And satellites are key to monitoring the sun and what's going on the sun every minute and every day. Let's come back down to Earth again. And let's talk a bit about the active and the passive sensors. We mentioned in the beginning, you can divide the sensors into active and passive. The active sensors, as I mentioned before, were more complicated because you need to transmit the signal out to the surface and get a response. So let's look at a few examples of these. One of them is to measure sea level rise. With the debate about climate change and the changes in temperature, in rainfall, in sea level, the only way we can really get a good measure of changes in sea level is using radars from space. So we have these satellites which are actually sending out a pulse of electromagnetic radiation, which gets reflected off the sea surface, comes back to the satellite, and looking at the time difference, we can say something about the altitude of the sea surface. And after doing this for a number of weeks at different places, we can actually get maps that we can see here, which actually show the relative height, sea level height, relative to the geoid, the Earth's kind of ellipsoid, where the greens are around about 0. And we can see here that there's red or pink areas. The sea level is actually about 40 to 80 centimeters higher than the reference. And the colder regions, in the polar regions where we have colder water, and colder water will take up a smaller volume, here we can actually have up to a meter below the geoid. So the sea level is not flat. It varies depending on temperature, wind patterns as well. In fact, the highest sea surface temperatures, the highest sea levels are actually in the western part of the Pacific Ocean, where we actually have also the trade winds, which are pushing the waters. But these are also very warm waters. And again, warm water will expand, takes up a little bit more volume. And so the warmer waters normally are higher up, closer to the satellite compared with the colder waters. But we can actually monitor this over time. And we've been doing this since the 1990s. And you can see from 1992, the different colors of different satellites. The satellite may only have a lifetime of maybe 10 years or so. So we need to cross-calibrate between satellites. But we can see here that we have an increase in sea level rise. The slope of this curve is about 3 millimeters per year. Doesn't seem that much, but if you multiply that by 10, we're talking about 3 centimeters per decade. And you can extrapolate for the rate per, per century. And it's predicted that by the end of this century, in another 80 years or so, this global sea levels may rise by up to a meter or so, which will have huge impacts on countries like Bangladesh, on Egypt, where a lot of low-lying areas around the deltas are within 1 meter of sea level. So satellites help us monitor the changes in sea level and can tell us if it's accelerating or decelerating, and which parts of the globe may be increasing more faster than others. We can also use these active sensors to look at wind speed at the surface, especially over the oceans. It's not very easy to remotely sense wind, but when we have strong winds, then we have larger waves in the ocean. And so if we send a radar signal or electromagnetic pulse to the surface, and it's a very smooth surface, then this will bounce off the surface and it won't return to the satellite. But if it's a very choppy sea and we have a lot of waves, then we'll get quite a lot of backscatter where the signal will come back to the satellite. So we can actually scan different angles and look at the backscatter of the signal coming from different angles. And as the satellite goes around the planet, we can actually map out not only the direction of the wind, which we see here with the arrows, but also the intensity of that wind, which has been calibrated to the height and the size of the waves. And so we can actually get information over the oceans of wind speed and direction from satellites. And here we can see a climatology, a monthly mean plot of wind speeds, where we can see here that in the tropical regions where we have actually what we call the doldrums and the ITCZ, we have actually fairly low intensity wind speeds. The blues here are around about zeros, but they're actually also going in the easterly, the trade winds going from east to west. The reds and the yellows are in the opposite direction. These are westerly winds and much stronger. So where we have the storms in the southern latitudes and the mid latitudes, we see much higher wind speeds. And this is taken over a monthly mean to get the average winds from satellites. We can also use radar, weather radar, precipitation radar from space. Today we have a satellite called the GPM, the Global Precipitation Mission, a joint US-Japanese mission. And here, again, you send down a radar beam. The wavelength has to be determined based on what you want to scatter off. If you want to scatter off the surface for wind, or you want to scatter off the droplets or ice for rain. And here you can see these are all LEO satellites, so they only take a kind of a snapshot of a slice going through the storm, but you get also distribution with altitude, so you can see the slice through this tropical storm, where you can actually see the vertical distribution of the rainfall, where here you can see 3 different parameters. You can see here the radar reflectivity inside. You can actually see the surface heights, and you can actually see the rainfall, the translation into rainfall from the satellite. We can also use LiDARs from space, so using a laser beam. A laser is instead of radar, which uses radio waves, LiDAR uses light or lasers. And again, because of the wavelength, you can get backscattered off small particles like smoke or aerosols and clouds, but you can only really see the top of the layer. So you can see here as the satellite is traveling, it gets this profile of these high particles, but underneath it, the dark blue, we don't see any information because there's no LiDAR which actually penetrates through. But you can actually detect, for example, smoke layers, and also say the altitude of the smoke and clouds at different locations around the globe. Okay, let's talk a bit about the passive remote sensing. These are the easier measurements where we're looking at just what's coming to our satellite, either reflected from the sun or emitted from the surface. Ocean temperatures, we saw about the ocean altitude, but if we just look at the black body radiation from the ocean, you can get an image like this showing the temperature of the surface of the ocean. Again, the warmest waters on the West Ocean. We have here the cooler temperatures and this cold tongue along the Galapagos Island. But we can actually take a box and monitor that over time, and also look at the trends in the sea surface temperature. This is from November 81 to January 2009, approximately 0.26 degrees C per decade, the warming seen in this part of the globe. And so this is also a tool which we can use to track the changes in the temperature of the global temperature. We can actually look at the color of the ocean to look at chlorophyll in the ocean, the actual biological activity in the ocean. And these zooplankton and phytoplankton in the ocean actually change the reflectivity of the ocean and the color of the ocean. And so we can actually see different regions of where we're having upwelling in the ocean, where we have a lot of biological activity. And this is used also for even fisheries, for people who go out fishing to see where you have the best biological activity in the ocean, and also to study the biosphere and the biomass in the oceans. Looking at surface characteristics, a big topic today is what we call smart cities or sustainable cities. The whole topic of urbanization. By 2050, we expect maybe 75% of the world's population to be living in cities. And we need to manage those cities and monitor them, how they're growing over time. We can see here an example from Las Vegas, the difference, image from satellite from 1984 to 2009, the huge growth. We can actually monitor the green areas and the temperature. At the right, we have Atlanta, Georgia. And on the bottom, we have a thermal image using basically infrared sensors. And you can see in red where we have the hottest temperatures, which are well aligned, where we have the buildup of the cities and the asphalt and the buildings. And the cooler temperatures in yellow are where we have more vegetation and trees and parks. And this is actually used to try to help design cities in better ways, because we know that when you have vegetation in the city, you have more parks, more trees, more green areas, you actually cool the city down because the solar radiation goes into evaporation, less into sensible heat and more into latent heat release from the vegetation. And so this can help us also for urban planning. In remote areas of the globe, like the tropical forests, we have big problems with deforestation. Not too many people live there, and those that do live there are not really reporting on what's happening. But these are really critical for the climate of the earth, because these rainforests are a huge storage of carbon from carbon dioxide, which is taken up through photosynthesis. And when we cut these forests down and replace them with agriculture, and we also burn them, we release this back into the atmosphere, the carbon, as carbon dioxide, and this is contributing also about 20 to 30% to global warming. If we look at these two satellite images, 1975 and 2009, exactly the same location. In the 1970s, they built this road into the rainforest. As soon as people have access, then they start to build other roads, and people moved in, built towns, and all the clear areas here on the right-hand side are where we've actually chopped down the forests for agriculture, for pastures, for cattle. And not only that, these are being burned. It's cheaper to burn it than to pay someone to take away the wood and maybe use it for furniture. And so this is becoming a big problem, and satellites are a key in monitoring the changes in the rainforests and the damage which is being done in Brazil, in Africa, in Indonesia to the rainforests as a function of time, and can be used then as a tool for policy, for discussions, for negotiations with these countries, which often need help because of poverty and other reasons. And the destruction of the forest is not because they want to destroy the forest, it's because they need to find solutions for the population to feed themselves, agriculture, and other needs. Fires is a big topic from space. As we looked at the Planck function and the Wien's displacement law, again, you can see the Earth's 300 degrees, more or less, the emission around 10 microns. But as the objects get hotter and hotter to the sun, the emissions are at higher at smaller wavelengths. If we look at a typical forest fire around about 1,000 degrees, the emission is around about 3 or 4 microns, the maximum emission. And therefore, if we want to detect forest fires from space, we need to build a sensor which will detect around about 3 microns, not 10 microns. And this is being used routinely to monitor what we call hotspots from space. These little red spots are the actual detected pixels, which are very hot and are radiating maybe above 1,000 degrees. And at the bottom, we can see a map of the whole globe. And this is really a global phenomenon. These little red dots are where we can detect fires. I think this is over an entire year. We can also animate this just for 1 year over Africa. You can see the vegetation and the changes of the seasons, but you can also see the fires in the red dots detected from space. These are man-made fires. 90% today of the fires on Earth are due to man-made fires, whether it's to clean areas after agriculture. You have similar fires and problems in India. After the harvest, people burn the fields to clean them, to get rid of pests. And so these are maybe small fires, but can be detected from space. There are seasonal fires as well. They're lit normally in the drier season. And when the rains come, then it's difficult to light the fires. So you can also see in Africa, there's a very seasonal distribution of where we see the fires, but we can monitor them very easily from space. Some other things we can do with satellites. This is monitoring the ice sheets. This actually is an interesting satellite because it's actually not using electromagnetic radiation. It's using gravity. The gray satellite, it's actually 2 satellites which are 1 or 2 kilometers apart with a laser beam between them, and they measure the pull of the Earth on the satellites. And if the mass of the Earth underneath it changes, then the height of these satellites will change slightly, and we can detect this. The mass of the Earth isn't changing much, but when we go over Antarctica, over Greenland, where we have 3 or 4 kilometers of ice, and this ice is melting, then the mass is actually decreasing as a function of time. And we can actually see that in Antarctica and Greenland. This is the mass in gigatons, the decrease from 2003 or 2 when the satellite was launched until today. We wouldn't be able to do this without satellites. The same as the sea ice over the North Pole where nobody lives. Only since 1979 do we have satellites which are going over the pole every day and we can see the dramatic decrease in the area covered by sea ice going from 1979 until today. These are data which we are using to show the politicians that the climate is changing, the Earth is changing, it's going to impact sea level rise. But without satellites, we'd actually be quite blind in the polar regions. We wouldn't have much data and what was going on. So satellites can also be used to monitoring pollution, air pollution. We can see here over China, but also ocean pollution, where not many people live. 70% of the planet is covered by the ocean. But oil spills, for example, when they're produced in the oceans, difficult to know who produced them, who's to blame, who's going to pay for the cleanup. Satellites can observe this on a daily basis to see who was there and send them the bill to clean up the mess in the oceans. Dust storms in Israel. Here, this is my home. I'm sitting over here at the moment. The Dead Sea, the Mediterranean. We have a lot of dust, and monitoring dust is also an important field using the satellites. The gases, we spoke about gases. So one of the poisonous gases in the atmosphere, mainly from burning of fossil fuel, but also biomass burning, is carbon monoxide. And here you can see the difference between 2000 and 2014. In fact, there is some good news that with carbon monoxide, we're actually seeing a decrease over time in the amount of pollution because we have various regulations, cleaning up the air, reducing air pollution in some countries. And so we're actually having a decrease in carbon monoxide. However, when we look at carbon dioxide, CO2, again, measurements from satellite over a one-year period from September 2014 to December 2015, looking at the absorption spectrum, we see a different picture. Things are going up and going up everywhere. These are measurements on the surface as well, from Hawaii to Alaska to the South Pole. These are long-lived gases, the carbon dioxide. They may have a lifetime of decades to hundreds of years, and therefore the seasonal cycle may be slightly different, but the trends are the same wherever we're looking. And again, satellites can be used to monitor the change in greenhouse gases over time. One of the success stories using satellite was the ozone hole. You've heard about the ozone depletion, the ozone hole. Well, the ozone hole was detected using satellites because it occurs mainly over Antarctica, again, where not many people live. Satellites flying over Antarctica detected that around about September, October every year, starting in the 1970s, we started to see this dramatic decrease in ozone. And you can see the amount of ozone here getting down to about 100 Dobson units, which occurred exactly at the same altitude where we normally have the ozone layer. So if we look at the profile with altitude over Antarctica, in the 1960s to 80, we have this peak. And then from the 1990s to 91, we see this dramatic decrease exactly where ozone should be, just disappears. And when we look from the satellite, we see this ozone hole. So the satellite observations, again, were key in bringing the politicians and the industry to ban the production of CFC 11 and 12 to try to replace them with HCFCs today. And so satellite observations and monitoring over long periods of time have a dramatic impact on policy decisions and international regulation. Finally, we'll show you two images which are close to my heart and to Dr. Guha's heart about lightning. We also have sensors to look at lightning around the planet. You can see this animation, which is over a 5-year period, not a specific year, but it shows you the migration of lightning with the sun. Southern hemisphere summer, or northern hemisphere summer has mainly lightning in the northern hemisphere. Southern hemisphere summer, it's mainly in the southern hemisphere. Interestingly, the lightning is mainly over the land areas. And we measure this from satellite mainly with optical sensors. Again, the actual flash of the lightning can be detected from satellite. And today we have our first geostationary satellite with a lightning sensor. This is the American GO-16. And here you can see an animation from 2017. The yellow flashes are the lightning detected. At the same time, we have the infrared image showing the clouds. There's tropical storm, tropical cyclone. Lightning telling us a lot of information about where we have the convection, the deepest clouds, electrical activity, how it changes as a function of time, space. And so combining different sensors from satellites, we can learn a lot about what's going on in the atmosphere of the Earth and on the Earth's surface itself. So I'm going to conclude here just to say that Earth observations from space, we can use satellites to monitor the surface conditions of the Earth, whether we're talking about urban heat islands and sustainable cities. We're looking at temperatures of the sea, of the land, ocean characteristics, chlorophyll in the oceans, sediments, vegetation changes, whether it's the forests or agriculture, snow and ice changes at the surface. We can also monitor the atmosphere, the atmospheric conditions, as I just showed you, ozone, the ozone hole, but also cloud cover, cloud type, the development of storms, aerosols, dust, pollution in the atmosphere, the temperature structure also of the atmosphere, which is being now done using GPS satellites as the source of the radiation and looking at how this changes during sunrise or the rise and set of the satellites as they're going, as the information is going through the atmosphere. And the energy budget of the Earth, which is also important by looking both at the incoming radiation from the sun, looking at the sun over its solar cycle, the different frequencies, wavelengths, and how this changes over time, but also the outgoing terrestrial radiation, which tells us something about the greenhouse effect, how much is being trapped inside the atmosphere and how much is actually making it out. So with that, I'll thank you very much. And we have a few minutes, another 5-10 minutes for questions. So if there are any questions, I'd be happy to answer. Thank you very much.
Thanks, Colin, for your nice presentation. It was very, we were actually glued to the presentation, and the topic of the FDP is sensor technology. So, but here also we are actually dealing with sensor technology, but it's a space-based sensor technology. Presentation was very nice, and open for discussion. So we have some questions here. You can see the chat window. Can you, Colin, see the chat window, or I can go ahead with the questions one by one?
Yes, I have a lot of questions here. Maybe you can pick a few that you saw were interesting, and you can just tell me which ones they are.
Yeah, so the first question that I request the participants to start typing it again, because there were many questions, but whatever I see right now is one person, Mr. Deshpande, asked, is it possible to trace crop variety using satellite sensing technology?
Crop variety.
Yes.
Yes, and more important than crop variety, it's possible to track the healthiness of the crop, or the stress, the water stress of the crops. Every plant has also a spectral fingerprint, like we showed with the gases in the atmosphere. And a lot of this, the absorption in the plants, is due to water in those plants. And so you can actually, and people have done this, you can build a library of spectra which are related to the reflectivity, or the both in the visible and in the infrared, for different species of agricultural plants, and therefore you can detect them from space. But you can also then see whether your plants are healthy or not, and know whether you need to irrigate or not, or you're irrigating too much, by looking at also the ratio of different parts of that spectrum. So when a vegetation is stressed and needs, in a drought condition, for example, there are differences between the changes in the infrared reflectivity and the visible reflectivity. So by looking at ratios of different wavelengths, you can say something about the healthiness of your crops.
Thank you, Colin. So we have another question from one person, but we don't know the name, but the question is interesting. Any sensors for predicting earthquakes?
Well, that's a good question, and a very controversial question, because some people, the question, first of all, can we predict earthquakes? Do we have any knowledge of that? So this is very controversial. There is some evidence that in the ionosphere, people see anomalies in electron content, also using GPS, before earthquakes occur. So if there are things which are occurring in the upper atmosphere in situ, so these are actually measuring, say, magnetic fields, particles, both in the ELF, VLF range, at the altitude of the satellite, people have detected anomalies linked to earthquakes. But there are many anomalies which also occur without the earthquake. And so MOMD is not very reliable. I don't think anything at the surface has been measured, for example, motion or emission, for example, of radon gas at the surface. Sometimes people say it occurs before satellites, but I'm not sure that can be measured from the satellite. So there are satellites, and there are even satellites at the moment, Chinese satellites, Russians, which claim that they are looking for precursors before earthquakes, but nobody has predicted an earthquake yet, given using this data. It's still a research topic.
Thank you.
Interesting.
Thank you. Yeah, it's a very challenging too. Yeah.
Yes.
So we have another question from Mr. Joydeep Dotto, who is asking how does the aurora forms in the polar region?
The aurora. So the aurora is formed by charged particles from the sun or in the radiation belts here. But let's say they start off all at the sun, electrons, protons, some heavy ions. Leaving the sun has this wind, the solar wind, which is traveling all the time outside from the wind, leaving the surface of the sun. These are charged particles, so they interact with the magnetic field of the Earth. The magnetic field acts like a huge shield. And so these particles, when they hit the magnetic field, they actually get diverted by the magnetic field, which comes into the North Pole and the South Pole. And so these particles only can come in to the lower atmosphere in the polar regions. When they come into the atmosphere around about 100, 200 kilometers above the surface, they start to interact with the gases in the atmosphere, nitrogen mainly, oxygen. And because of the energy of these particles, they can actually excite the atmospheric molecules, and therefore we have photons released both from oxygen, both atomic oxygen, molecular oxygen, nitrogen, and this gives off the different colors of the northern lights. So the green color you often see in pictures is actually from atomic oxygen. Depends on the energy. You can also have blues and you can have reds, but most of the aurora we see is actually from the excitation of atomic oxygen, around about 100, 150 kilometers above the ground, and along the magnetic field lines. That's why you often have this kind of curtain effect, the striation effect of the aurora, where these particles are coming down into the Earth along the magnetic field lines.
Thanks, Colin, for the nice explanation. And I think the answer was to the point. And Mr. Dotto, you can confirm whether you are satisfied with the answer in the chat box, if you can. We have another question from Jitumani Kalita, asking what are the materials used for the IR sensors?
What are the what?
What are the materials used for IR sensors?
Well, it can be just a simply infrared camera, but it obviously has to be made made in a way that it can withstand the conditions in space. You're basically putting your camera in a vacuum, and you also have very high and low temperatures, changes in temperature when it's being lit, when you have the sun shining on your satellite or when you're in the shadow of the Earth. So these have to be tested before launching, but you can you can purchase already IR cameras which are already tested and built for satellites. So you can have a very simple camera, actually, like you would have on the Earth, a thermal camera, or you can design it yourself where you have basically a detector which is sensitive only in a very specific wavelength, like the water vapor band, where we only at about 6 microns. So you can define your wavelengths and filter your signal just to get a certain wavelength. Or you can have a broadband camera, IR camera, which sees everything. But again, so it's not that complicated. The only complicated thing is it has to be sufficiently tested on the Earth in a vacuum chamber, in thermal chambers, that it will withstand the harsh conditions in space.
Thank you, Colin. So I don't have any more question on chat box, but now we have a few minutes left. So I request the participants, if you want to directly interact with Colin Price, you can just unmute your microphone and ask your question through this Meet platform. Okay, Colin. So I think your presentation is so fine that in the chat box we can see that it is really understandable. And this is a long program, 5-day program. People are getting exposed to different kinds of lectures, and this is really nice that we are having different spectrums of lectures that include sensor technology, from nanotechnology to biological sensors to now we have satellite sensors, and in the days forward we'll have many other lectures also. So but people have given lots of thanks, and I think your presentation was